My name is Taro Narahara. So I'm basically trained in mathematics and architecture before I came to NJIT. And right now I'm teaching mainly digital design. Today's topic, I'd like to talk about emergence. Emergence is the topic that I have been obsessed with for many years. And let me just show you a very simple example. This is a simulation of pedestrian crossing. So these little guys represent pedestrians. Then once you start running this application for a while, you start to see stripes between two movements of pedestrians. This is called a lane formation. Basically, they start to form most stable state. Most stable configuration. But what's interesting about this one is each agent has very simple local behaviors, and they don't really have any kind of global decision-making behaviors. Then once you start changing configuration, they start to find another steady state by themselves. But what's interesting is they don't really have any kind of intelligent systems. They locally make decisions, then gradually find globally cohesive patterns. So you can find this kind of behaviors in many natural systems, but rarely you can find this type of generative behavior in architecture, especially in modern professionally driven architecture. So my basic interest is apply computer algorithm for modeling self-organizing behavior to the design of architectural space. Then the first attempt based on this concept was visualization of human behavior. Then I had a chance to develop simple software that uses computational agent. Then these little guys, basically, it's not a simple animation. They have their own cognition to the space around it. Then they do basically stochastic decision making based on their surrounding conditions. Then, unlike engineering applications, I was very much interested in qualitative interactions. So it's not only egress simulation type of work, but also they basically can sense privacy or materiality and visibility. Those are the major factors that that directing their movement. Then other collective groups, they start to produce different kind of behaviors. Then if you change the layout of the room, they start behave differently. And it's not predefined animation. If you run this with different room, and every time it makes stochastic decisions, so you end up seeing slightly different result. But you run it a number of times, then gradually you can capture behavioral tendencies reside within the space. So this is basically a tool that can analyze spatial quality. So that was my basically first approach using the concept of emergence. Then a few years later, I was contacted by a Japanese software company, engineering company. Then I started collaborating with them, then implementing human pedestrian agent in their software packages. So this is in real time simulating the most busiest pedestrian crossing in Shibuya, Tokyo, Japan, using my agent in their program. So I basically worked on their SDK and producing software package with them. So I do a lot of collaboration with engineers and technical people. Another thing is I work on explore how we user can interact with digital environment. So this is basically I'm making a sensor-based interface, and directly you can access whatever happening in your computer. And another thing, it's basically experimental prototype, but architecture model usually very static, but by projecting some time-based medium, you can actually represent multiple scenarios. So using the single model, you can actually represent multiple different architecture scenarios. So those are experiments in user interface and interaction. And also a little bit about my teaching. I incorporate various kinds of sensors. One is Microsoft Kinect. It's a gaming device, but you can't underestimate this type of device. It's actually the most affordable depth sensor we can get. And I incorporate this in the classroom so a student can explore a different type of interaction. It's basically influencing computer environment from the physical body. And they're not really like a programmer, but they're learning how to implement this type of logic that's established by them. Another thing is a kinetic architecture. This is something I've been working with my students. So going back to main topic, self-organization, at some point I realized that I've been using this only for visualization and simulation of existing conditions. But why not using it for generative generation of design instances? So this application is slightly different, similar, but these little guys, agent, can influence and change the environment. Then all those changes in the environment actually changes the behavior of agent, and that change also trigger environmental changes. So it's kind of like a reciprocal relationship between agent and the environment. Then if you run that for a more realistic environment, you start to see this type of trail pattern emerges. Then if you implement building building generation pattern behaviors for agent, then apply that to actually existing environment, you can actually run the simulation. And what's great about this is it's not imposing any kind of existing template or typology of architecture. It's basically finding its own stable states based on the given minimum information. In this case, landform and environmental conditions. So that's advantage. Then I have another approach is, it's based on the same principle of emergence and self-organization, but I do take more physical approach. So this basically experimentation in architecture panels, but each one of them has its own intelligence, and they have their own sensing devices, so that they can find their most stable configuration rather bottom-up manner. There's no central component in it. They talk to each other locally, then try to define what's most efficient. Then advantage of this approach is basically it's very robust for dynamic changes. This piece basically I have very simple light sensors embedded on every pieces, but once you start changing the light sources, it start to reconfigure themselves dynamically. So it's not toward the predefined blueprints. It's adaptable, and that's the strength of this approach. Another physical application, I was a research assistant at the Harvard working with this robot, industrial robot. Then I was working with a bunch of students and faculty members there. Then first thing I did was writing a translator between robot and CAD environment that is really familiar with architecture students. So robots speak its own language. Then in order to produce for students to actually access this kind of geometry, they needed translator. So my software basically extract any kind of surfaces, then it's provide all kind of robot instruction. Then this is one instance I collaborated with several faculty member and students there. I basically provide the software for them. And then this looks kind of interesting. Everyone get happy, but but I realized this is only for convergence toward the predefined design scenario, and there's no dynamic adaptation for this piece. It's basically robot is just repeating the hard-coded instruction. So I wrote, it's again very simple experimentation, but this is a program that can stack bricks, but it's always making every step, it's making a stochastic decision based on really primary basic physics. Then it's try to find stable stacking patterns. So while it's running, robot actually thinking, and they try to find the new location. But it's a more dynamic dialogue between machine and us. And every time when you run it, you end up seeing slightly different result, but it's not the convergence word, the specific blueprint or goal. And okay, so it's still probably very conceptual stages, but I basically start finding some similarity and resemblance to natural scenarios. So title, basically obsoleting blueprints. That's my future goal, and still working within this paradigm. I'm welcome to work with a number of faculty members from outside of architecture as well. I'm really interested in opportunity to collaborate. So thank you very much. Thank you so much.